Welcome to lecture 26. In this lecture, we'll do some more examples of Faraday's law, and then we'll talk about the relationship between electric fields and magnetic fields. So in this example, we have a sliding bar on rails. It has a resistance of 6.6 ohms, and it's set in a magnetic field. We'd like to find the applied force required to move the bar to the right with a speed of 2 meters per second. So in order to find the applied force, we know we're going to need the current. In order to get the current, we know we're going to need the induced potential. So let's see what we can figure out here. If we move the bar to the right, what are we doing to the magnetic field? Well, we're making more magnetic field into the page. That's going to induce a magnetic field out. So the induced magnetic field will point out of the page like this. If we induce a magnetic field out of the page, we can use our right-hand rule to see that that gives us an induced current, which is in the counterclockwise direction. So we're going to get a current around this circuit in this direction. Okay, so that's what's happening. And Faraday's law or Lenz's law and Faraday's effect tell us all that. If we'd like to find that current, let's first find the induced potential. The magnitude of the induced potential is the change in flux with respect to time. Flux is equal to the magnetic field dotted with the area. Those two guys are perpendicular, so we're left with B times A. And the area of our loop, we've got B. The area of the loop is the length times the width. The width is down here in the horizontal direction. B and L are constants. So we've got B times L times dW dt. That's just the speed of the loop. That's your 2 meters per second. Okay, let's put in our numbers and calculate our induced potential. So our induced potential is the size of the magnetic field, 2.5 teslas, times the length of the bar that's moving in the field, 1.2 meters, times the velocity with which it moves, and that's a speed of 2 meters per second. So our induced potential is 6 volts. All right, next let's find the induced current. From Ohm's law, we know V equals IR, so I is the potential epsilon divided by the resistance R, 6 volts over 6.60 ohms. That gives us a current flowing through that loop of 0.909 amps. Okay, we'll spill over onto the next slide because this one is full, but next we'll be able to calculate the induced magnetic force. So now what we have is a bar moving to the right set in a magnetic field that's into the page. The current in that bar points up, so you can do your right-hand rule to see that there'd be an induced magnetic force, FB, that acts to the left. The size of that induced magnetic force is equal to ILB. So the current is 0.909 amps. The length is 1.2 meters. And the magnetic field is given as 2.50 teslas. So that gives us an induced magnetic force of 2.73 newtons. That force is a vector, and we know from our right-hand rule that it points left. Okay, we're close to the end, but this is not quite it. The problem asked, calculate the applied force required to move the bar to the right. The reason that bar moves to the right is because we pull on it with some applied force. It's moving with a constant speed. That tells us that the acceleration has to be 0. So the net force equals mass times acceleration. The net force is the magnetic force plus the applied force. Mass times acceleration is 0, so our magnetic force to the left, it's negative, plus our applied force, that's to the right, so it's positive. tells us that the magnitude of our applied force must be equal to the magnitude of the magnetic force, and the direction of that force is to the right so that it moves to the right. When we discussed solenoids, we said that an MRI was an application of a solenoid. It produces a changing magnetic field around your body. That induces magnetic fields in your muscle loops, which will induce a current. So let's ask, how big is this current that gets induced in your body by an MRI machine? Let's make a list of the things that were given. The problem says that the resistance of your muscle loop is about 4,800 ohms. The magnetic field drops from 1.6 teslas to 0 teslas. So we have an initial and a final magnetic field. That change takes 0.3 seconds. And our picture shows that our muscle loop is a circle with a radius of 4 centimeters. That means that the area of that loop is going to be pi r squared. To find our induced current, we're going to need our induced potential. So let's start with our induced potential. We know that induced potential is change in magnetic flux over time. Since we have two discrete points, we'll use the form of delta phi over delta t. Delta phi is going to be phi final, take away phi initial, over delta t. And phi, we remember, is magnetic field times area. The two vectors are parallel. So B dot A is B times A times cosine 0, or just B times A. So B final times area minus B initial times area over delta t. We take our area outside, minus B final minus B initial times pi times r squared over delta t. Okay, we can put our numbers in here now. Minus 0 minus 1.6 teslas times pi times 0.04 meters squared divided by delta t, which was 0.30 seconds, gives us an induced potential of 0.0268 volts. Pretty small potential. Got a pretty big resistance, so we anticipate that current's going to be small. To find our current, let's use Ohm's law. Ohm's law says that V equals IR. So I is the potential, the induced potential, epsilon, divided by the resistance. And we get a current of 5.59 times 10 to the minus 6 amps. So that is indeed a very small current induced in your body when you get an MRI. In this example, we have a long straight wire carrying a current of 1 amp and a conducting loop nearby, and that carries a current of 2 amps. Let's go through this step by step and see what we can find out as we go. Part A. Find the magnetic field at the left and right edges of the loop due to the wire itself. So our wire is carrying current, so it makes magnetic field. Here is the left edge of the loop. If we'd like to find the magnetic field here, we know that it makes big circles. So we come around in circles. To get the orientation, we do our right-hand rule. So it's coming out this way. At the loop itself, it's coming out of the page. Okay, so you've got to do your right-hand rule to find the direction. We've got some practice doing that already. So it's coming to the left and front, coming out of the page in the plane of the loop. If we'd like to find that magnetic field, so B on the left, the magnitude is mu naught times I1. We're using current I1 because we're asking what is the field made by the wire, over 2 pi times r, the distance, why don't we call that R1? R1 is 1 centimeter. So that's 4 pi times 10 to the minus 7 Tesla meters over amps times 1 amp, divided by 2 pi times the distance between the wire and the left edge, 0.01 meters. Gives a magnetic field of 2 times 10 to the minus 3 teslas. The direction is out of the page, so I'll pop in a coordinate system, x, y, and z. Out of the page is the positive z direction, so k hat. Okay, that's the left edge. What about the right edge? Well, the direction of the magnetic field is still going to be out of the page. So our B on our right edge, so over here is the right, is equal to mu naught times I1 over 2 pi times R2. R2 is the distance between the wire and the right edge. See that that's 2 centimeters. So 4 pi times 10 to the minus 7 Tesla meters over amps times 1 amp divided by 2 pi times 0.02 meters gives us a magnetic field of 1 times 10 to the minus 3 Teslas out of the page, or K hat. Okay, there's part A done. Part B says find the average magnetic force on each edge of the loop. I think actually I'll go on to a new slide for that one so I have lots of room. Now in part B, we want the magnetic force on the left and right edges of the loop. Let's do the left edge first. The magnetic force on the left edge is the current running through the left edge, that's I2, times the length of the left edge, crossed with the magnetic field that it's sitting in, we labeled that VL. So our direction of that force, we can find that with the right-hand rule if we wish, or we can do our vectors. Let's do the vector thing. So I2 is the current through that loop. It's moving downwards, and it has a magnitude of 2 amps. So we've got 2 amps. The length is shown in the picture as 4 centimeters, 0.04 meters. The direction is down. That's the negative y direction, so negative j hat. I'll just pop my negative right in front there. J hat. That's crossed with the magnetic field, which is 2 times 10 to the minus 3 Teslas out of the page, K hat. So that gives us minus 1.6 times 10 to the minus 6 newtons J cross K. J cross K is equal to I. And then if you did your right-hand rule, you would see that that points to the left, which matches our minus I that we found from the calculus. Okay, there's our F on the left side. Now let's do our F on the right-hand side. F on the right equals I2, the current in the loop, times L cross V of the right. The current is 2 amps. Our L is 4 meters. This time, we know that L is the same direction as the current. This time it points up. That's the positive I direction. Crossed with the magnetic field it's sitting in, that was 1 times 10 to the minus 3 Teslas times K hat. The magnetic field is weaker, so we expect that force to be smaller. And we get 0.80 times 10 to the minus 6 newtons. J cross K gives us I hat. So that force is to the right. Okay, so there's our force on the left and right edges of the loop. Part C we'll do next. Part C asks for the net force on the loop. So we've got the left and right dealt with. What about the top and bottom? So on the top, there's a magnetic field that points out of the page. There's a current that's coming to the right. So there's the current I2 on the top. What would be the direction of that force? If you do your right-hand rule, you should see that the force on the top part of the loop is going to point up. What about on the bottom part of the loop? Well, there's a magnetic field out of the page. The current is to the right. If you do your right-hand rule, you'll see that the force on the bottom points out of the page. Those two pieces of wire are exactly symmetric. They're the same length, same current, same field. The only different thing is the direction. So that tells us that the force on the top plus the force on the bottom equals 0. Those forces are equal and opposite. They cancel. Okay, so to find our net force then, we really just have to add together the left and right parts. Oops, I wrote R instead of F. There we go. That's close to good enough. And that gives us a net force of minus 0.80 times 10 to the minus 3 Teslas times I hat. Part D now asks us to find the magnetic moment of the loop. So remember that magnetic moment is current times area. This is information about the loop. So the current means the current flowing through the loop, I2. What is the area vector of the loop? Well, the magnitude of the area is length times width. So the length is 4 centimeters, the width is 1 centimeter. And the direction, you have to do your right-hand rule. You make a circle with your fingers that matches your I2. So your circle of your fingers comes around this way. You ask, what is your stuck-out thumb doing? And it should be pointing right at you. So when you make a circle that matches that loop direction, your stuck-out thumb should be sticking right in your face. That's a K hat. So our magnetic moment then is our current I2, 2 amps, times the length of the loop, 4 centimeters, times the width of the loop, 0.1 meters, or 1 centimeter in the K hat direction out of the page. Our magnetic moment is 8 times 10 to the minus 4 amps times meters squared, and that is in the K hat direction. Okay, I think we have enough room on this slide to do part E. Find the net torque on the loop. So the net torque is the magnetic moment of the loop crossed with the external magnetic field that it's sitting in. So mu here is of the loop, and that loop is sitting in a field created by the wire. Okay, we don't exactly know what the magnetic field is because it's changing at every point. The magnetic field on the left and right is different, but we do know that at every point, the direction of that magnetic field is K hat, always out of the page. And the direction of our mu vector is also K hat. So when we calculate our torque, the torque is going to be some magnitude times K hat crossed with K hat, that's equal to 0. Okay, so when your magnetic moment is parallel to your magnetic field, the torque is equal to 0. Part F asks, if the loop is free to move, what would its motion be? Well, let's stick with what we found in part E first. And part E said that the net torque is equal to 0. So that loop is definitely not going to rotate, not going to spin around. What about the net force? Because forces cause motion as well. Our net force, we had a big force on it towards the left. We had a small force on it towards the right. So our net force points towards the left. That means that it's going to accelerate towards the left. So that loop is going to be drawn towards the wire. Now the last part, G, is a Lenz's law question. If current I1 is switched off, what happens? So we want to switch off I1. So remember, current I1 made a magnetic field, B1, that pointed out of the page. That's what current I1 did. So if we switch off I1, that magnetic field B1, which was out of the page, goes to 0. So B1 out of page goes to 0. Well, if B1 is going to 0, that means Lenz's law is going to kick in. The induced magnetic field will act to maintain what we had before. So our change is that our field out of the page is disappearing. So our induced magnetic field will be out of the page. It wants to keep that magnetic field. So induced B will be out of the page. Okay, what kind of current does that induce? Well, the kind of current that induces is going to come around counterclockwise, and your right-hand rule shows you that that's true. So induced B is out of the page, induced current is counterclockwise. Well, that loop already has a current that's counterclockwise. So the induced current is going to be in the same direction as I2. So that tells us that the net current in the loop will increase. Okay, that's kind of a neat result. If we turn off current I1, we'll see current I2 jump up. In this problem, we have another slider problem, but rather than being in a horizontal direction, this one is free to move vertically. We want to show that a slide wire reaches a terminal speed if we release it from rest on these frictionless rails. So if we release it from rest, it's going to start to fall. If it starts to fall, we're getting an area with more magnetic field into the page. So increases B inward. That's going to induce a magnetic field outwards. So we can draw that if we wish. There's the induced field. Then your right-hand rule shows that that's going to induce a current counterclockwise. So your fingers curl to represent the magnetic field. So the current goes to the right in the bottom part, then goes up along the sides. There's your current induced. And that leads to an induced magnetic force, which will point straight up. Your thumb goes with your current, your index finger goes with your magnetic field, and your middle finger shows your force. When these two forces, the magnetic force and the gravitational force, when they're balanced, the acceleration will be zero and we'll get a terminal velocity. Let's find an expression for our induced magnetic force. So force is IL cross B. To find our I, we know that that's going to be the potential divided by the resistance. The potential we get from Faraday's law, d phi dt. Let's just find the magnitude. Equals d by dt. We'll go through this quickly because we've done this a bunch of times. B dot A. Those guys are parallel, so we've got d by dt, B times L times W. The area is the length times the width. So there's the length, there's the width. B and L are constants. dw dt, change in position over change in time, is the velocity of that sliding loop, BLV. There, it's a bit squished, but hopefully you can still see it. So we've got BLV over R. Okay, let's put this in our expression for our force. So our current is BLV over R. The length, oops, I kind of goofed with my symbols a little bit. I'm going to go back and fix those. So this length right here, I'm going to do that as a lowercase l. There. So now all of our symbols are the same. Okay, so the length is L. This length points to the right. It's in the direction of the current, so that would be the I hat direction. Crossed with the magnetic field, which is B, and that's into the page, that's the K hat direction. Oops, sorry, negative K hat. Into the page is negative K. So that gives us B squared L squared V over R. I cross negative K is J hat. And of course, you could have just done your right-hand rule, which we did up above too. Okay, so there's our magnetic force. Now we'll go on and find the expression for that terminal velocity. So we see that our magnetic force has a magnitude that's proportional to the speed. That tells us that the magnetic force is going to have a maximum value that'll be achieved when the magnetic force is equal to the gravitational force. And that's what our terminal velocity is. So when our magnetic force and our gravitational force, when they sum up to give 0, we have an acceleration of 0, which v equals constant, and that's the terminal velocity. So that means that the magnitude of the magnetic force, B squared L squared V over R, is equal to the magnitude of the weight, equals m times g. That gives us that the terminal velocity is m times g times r over b squared times L squared. So that is the terminal velocity that will be reached. Part B asked us to find the value. Let's put a circle around that because that's the expression that we were asked for in Part A. To find the value, the mass is 10 grams, 0.01 kilograms. G is 9.81. The resistance of the loop is 10 ohms. And dividing that by the magnetic field squared times the length of that slider squared, 0.2 meters squared, we get a value of 0.981 meters per second. This is a problem a lot like that previous example we just did, so I'm going to leave this one for you as a homework example. Won't do a video, but I will post the solution. Here's another example that's similar to one we did when we started this section about Lenz's law. So I think it might be a nice way to sum up and finish off this section. I'm going to leave it as a homework example. It'll be good review. I won't do a video, but I will post the answers.